Section 14.2 is titled with somebody's name you've seen before. This guy. What's his name? Do you remember how to say it? Euler. It's not Euler. It's Euler. It is Euler. Euler is a mathematician. Where did we see his stuff before? Do you remember? The Euler diagrams. Yeah, it was back in chapter 3, which was the second chapter that we did. And they were the circles that were embedded, but they weren't the Venn diagram circles. Remember that? It was section 3.5. So we're going to take a look at some more of Euler's work today. This is Euler Circuits. So a couple of different descriptions. We saw the descriptions of path and circuit before, but now we're going to do an Euler path and an Euler circuit. So an Euler path is a path that uses every edge of the graph exactly once. And an Euler circuit is a circuit that uses every edge exactly once. Okay, so we're going to take a look at a picture, right, a graph, and we're going to do something we did in the last one, where we're given a series of vertices and we're going to decide, is it an Euler path, is it an Euler circuit? Okay, so it has to be a path, right, which means we don't cross things twice. But to be an Euler path, it means we have to cross every edge once. An Euler circuit, again, starts and ends at the same point. But it's a path, which means it doesn't cross anything twice. And now it's going to cross everything exactly once. You got to get everything. Okay, all right, so here's our picture. If you need to draw it in there, do so. And it gives us a listing of points. A, B, E, D, A is our first one. And again, we're going to kind of make a mess of our diagrams to try and make it work with some colors. Yep, I've got it done there. So it goes from A to B, B to E, E to D, and D back to A. So this green is the sort of listing of vertices that it gave me. Is it, and it's specifically asking, an Euler circuit? No. Is it a circuit? Yes, it is a circuit. We haven't actually seen one, so this is a good one to see. We've seen it. Seen a circuit now. It's a circuit, but it's not an Euler circuit. Why not? Right. It's not an Euler circuit. Because it misses some edges. I'm going to put in parentheses just so that it's hopefully in your notes too, though. It is a circuit, though. All right. I wish I could erase the green without erasing everything. I don't know if I can. We're going to try. Wasn't too bad. Okay, it's back to where it was before. Now we have A, B, C, D, E, G. So let's do that one. A, B, B, C, whoops, oh, B, C. Oh, we failed so fast. What's the problem? There's no BC. It fails for other reasons too, by the way. Can somebody see another reason it's going to fail if we were able to have gotten far enough? We don't go to F. What else? There's no C. Which one? There's no CD. I have another failure where it tries to go from C to D. It doesn't end at the same points another one. There's so many reasons this one fails. It's a big time failure. So this is not a circuit. That's because it doesn't end at all in the same place. It does not return to A. And B does not go to C. And C does not go to D, you guys mentioned. So this isn't even a walk. If we don't have a walk, we don't have any of the other descriptions after that. Okay, you've got one more on the same screen. Mine's got to change screen since I ran out of space, but the picture's still there. Okay, so we're going to go through this one. AB, BE, EF, FG, GE, ED, DA, AE, EC, CA. We found one. It works. Notice it did cross through some of the vertices more than once. So we're going to have another description later that talks about what happens if we don't want to cross through the vertices more than once. But Euler's, you can do that. Its condition is just not crossing any of the paths more than once and making sure we get all the paths crossed. And we did, right? So this one is an Euler circuit. For all the reasons that it passes. And I'm going to put this note in here too so that hopefully, again, it appears in your notes. It's okay to repeat vertices. Okay to be repeating vertices. Okay, so let's look at Euler's theorem then. Euler's theorem says, suppose we have a connected graph. Okay, remember what connected means? You can get from one point to any other point in the graph somehow. You may have to repeat things or do weird stuff, but you can get there. Okay, so we have a connected graph. If the graph has an Euler circuit, then each vertex of the graph has an even degree. But also, the opposite works. If each vertex of the graph has even degree, then the graph has an Euler circuit. This is what we would call in mathematics an if and only if statement. If one direction works, then the other direction also works. That doesn't happen with all things. But it does work for this. Okay, one more thing to sort of make mention of. The condition at the beginning has to be checked. You really need to make sure you have a connected graph in order to make sure that this is going to work at all, right? We've got to have a connected graph for this to work. You can't just start jumping into counting degrees of things to see if things work. has to be connected. So here's an example of one. First, is it connected? Yes. You can get from any vertex to any other vertex without going off the paths, right? Off the edges. So it's connected. So the way we are going to be, or what we're being asked is if it has an Euler circuit. It doesn't really want us to find one. Okay, it just asks us if it's possible. So how do we decide, according to this theorem, if it's going to have an Euler circuit? We find the degrees of the points, and we see if they're all even, right? So let's do that. What's the degree of, we're going to find all the degrees, but what's the degree of point A? 3. D? 3. C? B? E? 4. Okay, so some are even, some are not. All it takes is one of them to not be even for this to fail, and we've got 4 of them, right? So it fails considerably. So there's no Euler circuit because A, B, C, and D are all odd degrees. So we're going to do another one that actually works, because I think you should see one that works too. It's a good idea. The directions are a little bit more expansive on this one. It says use Euler's theorem to determine if it has an Euler circuit. Then determine whether the graph has a circuit that visits each vertex exactly once, except to return to its starting point. If so, write down the circuit. There may be more than one correct answer. Okay, so first we need to decide if it has Euler circuits, which means we need to count the degrees, right? So, G, H, I, J, and K. Okay, will it have an Euler circuit? Yes, it will. So, this has an Euler circuit. The second question about starting and ending and crossing through points, though, it doesn't work. It doesn't work because I, no matter where you start, you're going to have to cross through I twice. If I start at I can go around one side of the bow tie, but then I have to come back to I before I go around the other side, right? If I don't, if I start at, say, G and I cross through I to get to K and go up and over, I still have to come back through I. So no matter where I start, the second question that I'm being asked will not be possible to be found. And we'll stop there for